Ever wondered about the magic behind predicting unknown spatial data points using observed data? That's universal Kriging for you. Welcome to the intriguing world of universal Kriging, a marvel of geostatistics that's akin to having a crystal ball for spatial data. It's a sophisticated estimation method that allows us to make educated guesses about unobserved locations based on what we know from observed data points. Imagine you're standing in a vast landscape with a handful of geographical data points scattered around. You know the exact details of these points, but what about the vast spaces in between? This is where universal Kriging steps in, acting like a bridge to fill in the gaps and give us a comprehensive picture of the entire landscape. But what sets universal Kriging apart from its predecessor, ordinary Kriging? Well, it's all about flexibility and adaptability. While ordinary Kriging works well for stationary data, where patterns and trends remain constant over space, universal Kriging shines when dealing with non-stationary data. It's like having a multi-tool in your geostatistics toolbox, capable of handling varying trends and patterns across different spatial scales. The importance of universal Kriging is immense, especially in the realm of geoscience. It aids in the prediction of essential geological variables, such as mineral content, groundwater levels, and soil composition, to name a few. It's a method that helps in making informed decisions, whether it's about where to dig a well or how to manage soil nutrients for agricultural purposes. In essence, universal Kriging is a cornerstone of modern geostatistics, a method that takes the known and uses it to illuminate the unknown. It's a process that mirrors the very spirit of scientific inquiry, always probing, always questioning, and always seeking to uncover the mysteries of the world around us. So, are you ready to delve into the specifics of universal Kriging? Hold on to your curiosity. Let's get the basics straight. Universal Kriging isn't as complex as it sounds once you understand the fundamentals. Kriging, at its core, is an estimation method that takes advantage of the spatial correlation between data points. It's like a treasure map of sorts. If you find a gold nugget here, chances are you'll find another not too far away. This concept is known as spatial autocorrelation, the idea that values at nearby locations are more likely to be similar than values at distant locations. Now, imagine you're a miner with a handful of gold nuggets, but you want to know where to find the mother lode. You'd start by mapping out where you found gold before, and then use Kriging to estimate where you might find more. Essentially, Kriging helps to predict unknown values based on the known values around them. But what about universal Kriging? Well, it's like Kriging with a twist. While ordinary Kriging only considers the spatial correlation between data points, universal Kriging goes a step further. It introduces a deterministic component, a mathematical function that describes a trend over the entire study area. Think of it this way: if ordinary Kriging is like trying to predict the weather based on what it was like yesterday, universal Kriging is like also considering the time of year and the general climate of the area. It's not just about what's nearby, but also about the larger trends at play. In the world of geostatistics, this deterministic component is a game changer. It allows us to account for global trends, like the gradual increase in temperature as you move towards the equator, or the way mountain ranges can impact rainfall. By considering both local and global patterns, universal Kriging provides a more accurate and nuanced estimation. Now that you've got the basics down, let's explore how universal Kriging works in practice. Universal Kriging, like any good recipe, follows a step-by-step process. Now let's dive into the methodological waters of universal Kriging. It's a journey of 3 main steps: creating a semi-variogram, calculating weights, and estimating unknown data points. Each one of these steps is a crucial ingredient in the recipe of geostatistical prediction. First, let's prepare our semi-variogram. Think of this as a map that illustrates the spatial relationship between data points. It's a graph that shows how dissimilar data points are, based on the distance between them. So, the closer the points, the more similar they are, and vice versa. This graph is created by plotting the semivariance against the separation distance. The semivariance is a measure of how much values differ as a function of distance. It essentially helps us understand how the spatial pattern of our data changes with distance. The semi-variogram, therefore, is the backbone for the spatial prediction that universal Kriging will perform. Next, it's time to calculate the weights. This is the seasoning that gives our recipe its unique flavor. The weights in universal Kriging are calculated using a matrix equation that takes into account both the semivariogram and the deterministic trend. The deterministic trend is a predictable pattern in the data that can be explained by one or more independent variables. The weights are then used to balance the influence of each data point in the prediction of unobserved locations. The idea is to assign more weight to the data points that are closer to the location we want to predict. Finally, we're ready to estimate the unknown data points. This is the final step, the presentation of our dish. Here, we'll use the weights calculated in the previous step to estimate the value of an unknown data point. We do this by taking a weighted average of the known data points. The calculated weights determine the contribution of each known point to the prediction of the unknown one. It's a bit like asking all your known data points to vote on what they think the value of the unknown point should be, with each point's vote weighted based on its spatial relationship and deterministic trend. Now, an important thing to remember is that universal Kriging doesn't just provide a single estimate for each unknown location. It also gives us a measure of the uncertainty associated with that estimate. This is called the Kriging variance, and it's a measure of the prediction error. It tells us how confident we can be in our predictions, adding another layer of information to our geostatistical analysis. See, it's a systematic process that takes into account both the spatial relationship and the deterministic trend. This is the magic of universal Kriging. It's a method that not only gives us a prediction for unknown data points, but also tells us how much we should trust that prediction. It's a recipe that delivers not just a dish, but a full dining experience. Now that you understand how universal Kriging works, you might be wondering, where do we use it? Well, let's dive in and explore the practical applications of this fascinating technique. To start with, universal Kriging plays a pivotal role in environmental science. Researchers use it to model spatial distribution of pollutants in the air, soil, or water. By doing so, they can predict pollution levels in unmonitored areas and take necessary action to protect our environment. Another field where universal Kriging comes in handy is mining. It's not always practical or economical to dig up every square inch of land in search of valuable minerals, so mining engineers use universal Kriging to estimate the location and quantity of mineral deposits, such as gold or diamonds, based on the data from sampled locations. This technique not only saves time and resources, but also minimizes environmental disruption. Moving on to agriculture, universal Kriging is a powerful tool for farmers and agronomists. Imagine a large farm with varying soil quality across its expanse. It's impractical to test every patch of soil individually. But with universal Kriging, farmers can predict the spatial distribution of soil nutrients based on a few sample data points. This allows them to apply fertilizers more efficiently and boost crop yield while minimizing waste and environmental impact. In the realm of public health, universal Kriging is used to map disease prevalence and identify potential hotspots. This aids in strategic planning of healthcare resources and timely intervention in affected areas. Similarly, in meteorology, it helps in predicting weather patterns and forecasting natural disasters, thereby aiding in timely evacuation and planning of relief measures. Universal Kriging is not confined to these fields alone. It's used in a variety of other sectors, including real estate, urban planning, and even wildlife conservation. Its ability to make accurate predictions based on limited data makes it a valuable tool in the modern world. From predicting soil nutrients to estimating gold deposits, universal Kriging has quite the range of applications, doesn't it? We've journeyed through the world of universal Kriging together, haven't we? We embarked on this adventure by entering the intriguing world of universal Kriging, a statistical technique that is as compelling as it is complex. From there, we dove into the basics, understanding the fundamentals of this method, the heart of geostatistics. It's not just about numbers, it's about the relationships and patterns they reveal. Then, we rolled up our sleeves and dug into the step-by-step process, painting a detailed picture of how it all comes together. We saw how universal Kriging is not a blunt tool, but rather a precise instrument that accounts for the spatial correlation and non-stationarity in data. And finally, we explored the practical applications of universal Kriging. From environmental science to the oil and gas industry, its uses are as varied as they are impactful. With that, we wrap up our exploration of universal Kriging. Next time you see a spatial data prediction, you'll know a little bit more about the process behind it.